coming up now, we have our industry panel. So I'm going to introduce our speakers. So you all can come off of, turn your videos on if you're comfortable, and then when I introduce you, you can go ahead and come off mute and give your slides. And we have them here on our side. So if you need us to push them, you can. But otherwise, I'll allow you to take over and push your own slides as well. So a reminder to the rest of the audience, you can put your questions in now so the speakers can address them sort of in the chat, or it can be a part of the Q&A that we have after speakers have had a chance to give their presentations. So I'm going to go in the order of the program, which means I'll be starting with Dean. Yes, and I see we've got Dean, so you can come off mute now and check that. Dr. Dean Bergman is the Director of Strategy and Development at Honeybee Robotics Exploration System. Works a lot on the mission risk manager. He was a mission risk manager for the Resource Prospector Lunar rover mission out of NASA Ames. Did his postdoctoral fellowship there, where he did diagnostic methods for autonomously detecting faults in interplanetary drilling missions. So some great experience from that. And PhD in aerospace from USC. Where he focused on modeling of large, novel deployable space structures. So Dean, I'll let you take it away.
Great, thanks, Wes, and hi, everybody, and thanks for having me. Let's share. Let's do that one. Okay, so I've just put a couple of slides together, just something to look at while I talk a little bit. Not a whole lot of new stuff here. If you've listened to a Honeybee presentation on power systems or listened to one of my panels before, then this is nothing new. But as Wes said, I'm Dean Bergman. I'm the Director of Strategy and Development at Honeybee Robotics, specifically for our California office, where we focus on exploration systems. So we're one of the 3 providers for the lunar vertical solar array technology. So what I'm showing here is our version of it, and it's the LAMPS system. So I'm not going to go too much into it because most of you have probably seen it before, but feel free to ask me more questions if you have any. But generally speaking, when we're talking about redundancy or reliability, there's 2 sides of the coin that we look at. The first side is for a single system, and that's where we're really good and shown a lot of our expertise, where you design something, have the selective redundancy, and do all of the testing to make sure that your system is reliable in your flight mission. So, some examples that we have are our systems on the Mars rovers, each of them, surviving a decade. It's way longer than the design life. And that's just, from the process that we follow, the process that NASA follows, that enables these long duration missions to survive a long time. The other side of it, which is a lot of what's been mentioned in these sessions, is the putting a whole grid out there. So you don't just have one system to rely on. You have multiple systems tethered together that work together to provide reliable power, and that includes multiple companies. We don't say that we're going to be the only company to provide power on the moon. We are well aware of the other 2 companies, and they are excellent, and we expect to integrate with their systems to provide dissimilar redundancy, which is important. And then, what was just mentioned, standards. That's something we've been working on a lot with our dust-tolerant connector. And then we've also been looking at, standard cabling. And we're very excited for Astrobotic that they've actually got a fly a mission to run some power cables on the moon, because this is going to be a huge issue. So We're excited to see what they have to bring and what they're going to show on the moon, and we'll learn from that and we'll all grow together. So it's all very exciting. So yeah, happy to answer more questions during the panel. But yeah, thanks for having me.
Great, thanks. And a reminder, you can put the questions into the Q&A. That's usually the easiest way to make sure that they go to everybody. So next up, I have Joe Halakna. So Joe started as a mechanical engineer and plant engineer manager on the AP1000 design. And he's done work for over a decade before transitioning now into reactor business development and advanced reactor engineering. And for the last 5 years, he's been doing a lot with eVinci heat pipe microreactor. So leading engineers and researchers on the reactor design, general nuclear systems engineering, materials research, and so on. So he comes from bachelor's in mechanical engineering from Penn State, master's and MBA from University of Pittsburgh. So Joe, if you are ready, you can come off of mute and give some of your insights in your intro.
All right, yep, on the mute button. All right, let me share my slides here. Thanks, Wes, for the introduction. Let's see, so I jump back.
Yep, looks good.
Yeah. All right, so again, Joe Lackna, I'm our chief technologist focused on our eVinci microreactor and our space reactor technology here at Westinghouse. Just to show again the portfolio, I spent most of my early career days on our AP1000 product and engineering, and again have been transitioning into our microreactor. And again, as we look at space and the synergies there, and I'll talk about that on the next slide or two. But again, this is Westinghouse obviously has a portfolio of solutions, and one of the things that we bring to the table is the advantage of, again, we can look for space to take pieces and parts of all these technology developments and all these products, ultimately to deliver the most reliable product for space at the end of the day. So our eVinci microreactor really, again, heritage really goes back to space originally. In 2015 timeline, though, we really started looking at, all right, how do I take that? And we had various partnerships, specifically with Los Alamos National Lab, and then really looked at, all right, how do we commercialize terrestrially that technology? And so from 2018 through 2021 timeframe, we were very focused on that. But again, a lot of now we really have the opportunity though to take it back again, and we've been we're obviously one of the teams on the fission surface power project, and again a lot of synergies from our own technology and research development and application that we've been able to drive into that and leverage from the development that the national labs and NASA and a lot of the other teams have obviously developed over decades, going back through Prometheus and then the GMO projects. So you can see at some of the variations and designs that we've done there, and some of our background, and again, I'll update this a little bit older, but for a lot of the things that we've now done in the early 2023 that are leading our commercial team, up through what is going to be our hallmark here of a nuclear test reactor. Just a little bit of background again, as what we refer to as eVinci, really our terrestrial design versus our space reactor design. But again, there's a lot of synergies in the technology, the design, the controls aspect, how we're going to form a grid, our load follow capabilities. Really, those are things I think that are very important for the grid reliability that we'll be establishing through these types of programs. You can see they're just our baseline power levels. Again, there's a lot of scalability here from our, again, kilowatt level all the way up to the megawatt level, and being able to, again, drive a lot of the technology, the materials, the research and development there, all of these things that we're doing and testing that we're doing. We're looking at, all right, how do I take this terrestrial technology, but add on, we talked about a lot of the lunar environment challenges, and again, add on those additional parameters to make sure our materials and everything are going to be qualified to last the duration of these missions. So really the hallmark for us is heat pipes. That's our technology that we focused on and again, was originally, conceptualized for the very reasons that we wanted to terrestrialize this technology, the reliability, the resiliency, really the mission assurance that we can have in the operation of these, eliminating those fault potentials as much as possible, and a lot of the different failure modes and effects that go into the fact that we're not going to have, the opportunity as nearly as we would terrestrially to maintain and operate these reactors. But it is part of our business development and strategy for even our commercial plants for our eventually microreactor, where again, we're targeting niche markets, off-grid, edge-of-grid, remote environments, and looking to deliver them, in that case, an 8 to 10 year solution, maintenance-free with limited operations and limited accessibility. So a lot of our, again, programs have focused on that already, and we're able to leverage that. And there'll be one talk later on, how we approach reliability in our systems, and one of the other short format talks. But heat pipes is centered for us. It's our passive capillary flow driven heat pipes. That's part of our tech transfer history with Los Alamos. And again, things that we've done to continue to automate and manufacture. We've done numerous test programs now and delivered those heat pipes for different agencies and labs to test, in addition to our own laboratories that we're doing in terms of developing and ultimately going to be reaching here over the next year the ability to manufacture thousands of heat pipes per year capacity out of our manufacturing facilities. And just so this is timeline, not specific to space, but again, just shows our technology development for eVinci and where we're heading from a licensing perspective and a manufacturing perspective, from design really through component fabrication and testing, through a nuclear test reactor program, which then will lead into our commercial terrestrial programs. We see a lot of opportunity to benchmark our analyses, and really being able to use data across our programs to drive synergies between the terrestrial and space applications that we're driving here. All right, so that's all for slides. Back to you, Wes.
Great, thank you very much. Thank you very much, Joe. Next up, we have Luis Carrillo. Forgive me if I didn't roll my R's or get that quite right. You can definitely let me know. He is the chief architect of Lunar Exploration Campaign at Lockheed Martin, where he advises a variety of programs within Human Exploration Campaign, including non-terrestrial power distribution and human habitation architectures, with recent work focusing on systems of systems modeling for lunar infrastructure, something we very much appreciate here. He's a master's holder from Thayer School of Engineering at Dartmouth, and both bachelors of engineering and science in engineering and physics from Dartmouth as well. So Luis, go ahead. You're welcome to share your screen and take over.
Sure thing. And I will say you did get it closer than most. Let me know if you can see.
It looks good.
All right. Great. Thank you, Wes. So to start, I probably don't need to emphasize in this forum that power is the fundamental backbone and one of the central enablers of the futuristic lunar economy. So I'll refrain from hammering that point, which I assume represents localized consensus. In this functional area, Lockheed Martin has multiple technology development programs presently underway. We're developing fission surface power as a source of continuous high power on the lunar surface, with an initial design capability of 40 kilowatts. We were down selected for the option period to build and test a VSAT prototype. And that means we're the only supplier presently working both nuclear and photovoltaic-based power generation elements. We're developing a lunar mobility vehicle, noting that its mobility features, payload capacity, and mechanisms directly support PMAD integration and installation. We're also developing something we call LEAP, the Lunar Economy Analysis Platform, used to analyze and characterize the behavior of the cislunar economy as a highly verticalized integrated system of systems. And we're also developing PMAD technologies, including a GaN-based DC-DC converter, just being one of those efforts. Okay, so this is one of many, I don't doubt, vision of how the lunar surface power architecture might look in the future. And I know, and there's a lot on this chart, but one important takeaway is that while we're at the start, we should be designing systems in a way that has the endpoint in mind. And we see this system as evolving both over time and over distance, initially starting with Artemis Base Camp and evolving to support both surface and crater ISRU production, and eventually to a global industrial context that that John had talked about yesterday. And so we may not ultimately realize that full global distribution context, but at a minimum, we're designing to account for that operational scalability potential. It's also worth noting that while this is this interconnected grid, there's no reason, especially during initial growth, that we wouldn't expect early deployment of independent microgrids or nanogrids at different locations. Although in the indefinite future, we would expect that we'd be able to leverage system efficiencies by interconnecting these over time. Okay, so what are the core requirements of the lunar surface power grid system designs? And we've been talking about a lot. So for one, we want our grid architecture to be sustainable. And in the context of sustainability, our system should be effective, efficient, and resilient. And the context of these discussions are focused on reliability. And so we're really talking about effectivity and resiliency. So I'll focus on those. So by effective, we mean that it does what it's supposed to do, deliver the amount of power needed to the places that need that power. But it also means that it doesn't do the things that it was not intended to do. And that includes minimization of unintended negative consequences. So for resiliency, there are a variety of ways that this can be decomposed. Usually I hear this as decomposing to robustness, continuing to work over a wide range of non-ideal circumstances, anti-fragile, responding to stressors and not degraded by low probability events, and adaptive, the capacity to learn with increased execution time and continued operations. And this doesn't have to be autonomy. Previously we were talking about thinking outside the box, but sometimes when you draw the system context diagram, you can put a thinking human in the box. So now, if we say that we want a reliable system, there are effectivity and resiliency threads that we trace through, and it's important to understand how that gets decomposed, so that we know how to implement it and that we know how to measure it. So a reliable system should be predictable, should exhibit known behaviors, and this includes graceful downstating in faulted conditions. It should be robust, operate nominally over a wide range of dynamic system configurations, available. It should have a low percentage of time in a non-operational state. And when it is available, you want to be able to depend upon it. It should have a high probability of meeting all requirements. And across that performance, you don't want it to degrade over time. Okay, so if we can understand our requirements here, how should we think about how we go about designing this system? So for one, and I'm happy to hear that this has been said many times over the recent discussions and then over the last yesterday and this morning, but we need to be thinking about interface standards, and they should be consistent with OSA, the Open System Architecture Principles. Broadly, one thing we don't want is different hardware solutions for different deployment configurations, and we should be implementing designs that are extensible to different topologies that we envision needing to leverage those system efficiencies. And there are kind of 2 points here. These next 2 points I do want to really hammer. So we need to protect against and address grid blackouts and islanding. I was happy to hear that also earlier this morning. If we lose power to an expensive science element for PSR, we lose that hardware. If we lose power to human habitation, crew members can die. And so we need to think about the design of a grid and sufficient fault responses and redundancy that enable continuous power and graceful downstating. And classifying the operational needs of these different types of loads we have on the grid will help us understand how to implement that effectively. There's also been a lot of conversation that's focused at the component and part level, and it's tempting to put a lot of our attention on the first problem. But when we're developing a grid with multiple power generation sources, the complexity of the power management problem increases non-linearly. The thing that's more likely to be a problem in the future is power management failures. The inability of the grid to pull power from the correct generation and energy storage elements in time to satisfy required loads. And we should also be designing for Black start, building harder with grid forming requirements. Parallelization in this context is an aspect of how we would implement modularity in system design. One thing that we don't want is to get to 100 kilowatt grid capacity and then need to a whole new system design. The systems we deploy should be operationally scalable and consistent with that last bullet. And lastly, we should be designing PMAD that has low attrition and high reuse. The one thing that we know about how the grid will look over time is that it will be different from what we thought it was going to look like. And designing for architecture flexibility will pay dividends here and reduce the overall system cost over time. And lastly, we recently published the IEEE paper at IEEE Era earlier this year on lunar surface power architecture concepts. And if you're interested in hearing a little bit more on our relevant perspectives on the topic, feel free to check out the paper. Back to you, Wes. Thank you.
Great, thank you. Some fantastic content in there. I'm glad to hear that a lot of the comments are sort of resonating. It's actually quite a nice thing when we all have the same sorts of ideas of how we need to move this thing forward. All right, so next up we have Dan Hendrickson. Dan Hendrickson serves as the Vice President of Business Development for Astrobotic. So congratulations on your recent award as well. And I'll note that all of the speakers today have active programs going on right now for our lunar surface return. And for Astrobotic, which is a lunar logistics company based in Pittsburgh, Dan leads the growth initiatives for the company, including those for lunar delivery and power. So prior to Astrobotic, he was the Director of Civil and Commercial Space Systems at the Aerospace Industries Association, which was a council of more than 50 US space companies to provide government guidance on key space industry views. So Dan, I'll let you take over now, and excited to see what you've got for us.
Thanks very much, Wes, and thanks very much for the inclusion in today's panel. Can you see the slides?
Looks good.
Great. All right, very good. Well, thanks very much. So as mentioned, my name is Dan Hendrickson with Astrobotic. We're a Pittsburgh-based lunar logistics company, as Wes mentioned. We've been in business since 2007, and we're perhaps most well known for our lunar delivery services. And it's really out of those delivery services that we came to appreciate the need for power and why we're making investments and putting considerable effort in the development of a program that we're calling LUNAGRID, which I'll describe a little bit more here in a moment. But just to give you a little bit of context for those that may not be familiar, as a lunar logistics company, we're starting with payload delivery to the moon with our uncrewed robotic lunar landers, Peregrine and Griffin. And then we're extending that delivery service out across the surface with mobility assets, namely wheeled rovers at the small scale called cube rovers, and then medium and larger size rovers to follow. So we have a manifest of missions that you can see on the right, just to give folks the quick update on both of those lander missions, because I think folks might want to be updated on that. Peregrine is ready for flight. It's carrying 16 customers from around the world, 21 different payloads that have been integrated. We're just now waiting for the Vulcan Centaur launch vehicle to be ready to receive Peregrine. So it's here in Pittsburgh in the clean room, completely finished and ready to go. We're just waiting for the green light to ship it down to the Cape. And then next to it, the Griffin lander is being integrated. This is a photo of the flight model of the vehicle coming together. That's going to be carrying the NASA Viper rover to the South Pole of the Moon to Nobile Crater, where they'll be doing the first ground truth measurements of lunar water ice in permanently showered regions there. So a very historic and exciting mission with two landers in the clean room, one complete and Griffin coming together right now. So as everyone on this conference is aware, power is everything on the moon. And so we have come to appreciate that from the perspective of the customers that we work with. 14 days of operation on the surface with uncrewed robotic landers is exciting. It's historic, it's groundbreaking. Obviously, the US hasn't been back to the surface in 50 years, but it's not enough. We've got to solve or ultimately mitigate the tyranny of the lunar night. And so with that in mind and with our customers in mind, we're developing LUNAGRID, which is a complete end-to-end service. It provides power generation and distribution The nodes within LUNAGRID itself are designed to survive the lunar night and then to provide power on the order of tens of kilowatts to surface assets in the kilometer scale of the area where LUNAGRID is located to provide multi-year operations at the lunar poles. We're planning to start LUNAGRID operation at the South Pole because that seems to be where all the action is in the near term. And so this is a look at the LUNAGRID architecture that we are looking to build over time. The first deployment you can see in the upper right corner is a fully self-contained starter LUNAGRID. So the LUNAGRID first mission includes a VSAT integrated onto a Griffin lander. And then coming out from that node are cables attached to a cube rover that carries a wireless charger. And so you can kind of think of the cube rovers almost as a mobile power plug, bringing power to surface assets in the area. And again, this is on the kilometer scale. So we're intending for these cables to be on the order of kilometers in length to be able to provide power in the vicinity. You might also note that there's multiple identical VSATs in the vicinity of this first deployment. So when it comes to reliability, we're big fans of redundancy and having identical systems deployed over and over again. We'd like to have each asset survive on the order of a decade, but if you have multiple VSAT towers, we really are big believers in that as a major mechanism for encouraging reliability, as well as to be able to bring in replacements over time, recognizing that maintenance on the lunar surface is going to be incredibly challenging, certainly for astronauts, in other ways even more challenging for robotic services and robotic systems. And so if you can deploy VSAT towers over time, have them be identical and delivered on CLIP style missions, there's a real advantage, we think, in over time. You'll also note that each of these VSAT towers, again, has cube rovers carrying wireless chargers, so that extends the coverage and the capability of LUNAGRID to reach more assets, to increase the sort of sphere of influence and operation that LUNAGRID and hopefully operations like Artemis Space Camp will have over time. It's also perhaps worth noting that each of the elements that you see on the screen here is now funded for development. There's really no element of LUNAGRID that's waiting to be funded or waiting to be proposed. All aspects are under development right now with actual real funding. So obviously Griffin, as the lander delivery vehicle, will be flying the NASA Viper rover. So that's in work right now and being developed and built. The VSATs, we're all aware, I think, on this conference that VSATs are well underway. We're one of the VSAT contractors, along with the other two companies that were selected by NASA. Cube rovers are a technology that's been advanced and done hand in hand with STMD over time. And we're going to actually be flying the first cube rovers here in just a very short number of years. And then wireless chargers, also a prior tipping point. And then, as has been mentioned here on the call, we also were awarded a new tipping point, which I'll highlight a little bit more later, but the cables are a major aspect, along with grid electronics. So that's going to be a major focus of that tipping point, and really the last sort of keystone element that needs to come together from a development perspective for LUNAGRID to ultimately be deployed and hopefully be successful. We see a lot of advantages in our mind with the LUNAGRID approach. Perhaps most importantly, it's deployable soon. We're big fans of the FSP program. We're actually partnered with Westinghouse on that. We're excited to support that program and that project. But in the near term, we really feel like vertical solar array technology is the right platform to get US presence to the moon as soon as possible, quickly, and then bring FSP online into LUNAGRID over time. So we really put an emphasis on speed, and we really believe that the vertical arrays help us do that. Each node is designed to survive the lunar night and help assets in the area to survive the lunar night. We also think it's a huge advantage to have LUNAGRID systems that are deployable on CLIPS missions. So we're wanting to utilize delivery mechanisms and systems that exist today, or at least are being developed and built today, rather than waiting on other systems that could come online in the future. And so again, with that emphasis on speed and practicality. The system, as noted, is scalable and extends coverage with that scalability. It makes the power mobile with the wireless chargers on the cube rovers. So it really doesn't matter what surface asset is utilizing the power, as long as they have a compatible 100 or 400 watt wireless charger receiving node on the other side, then they're able to utilize LUNAGRID, which also allows you to almost think of this in a future-proofing manner, in the sense that not every asset has to rely on LUNAGRID to start, but if they have a compatible wireless charger in the future, could make use of LUNAGRID. And then notably, we think it's an exciting opportunity to move power to the commercial sector, hopefully one day even get to the stage where we're charging dollars per watt ultimately on the surface. And as I mentioned earlier, we're excited to make LUNAGRID a power agnostic service over time, to be able to incorporate FSP, because we do think that's an important capability and element for the future on the moon and beyond, extending from the moon to Mars has been outlined in NASA's moon to Mars objectives. And so we see this as a system that can incorporate FSP as it comes online. So we think it really holds a lot of promise for utilization on a variety of fronts: decadal science missions like a Farsight telescope, CLIPS missions, and Artemis Base Camp ultimately. I'll just close by highlighting our Tipping Point Award, which has been mentioned. Again, thanks for the shout outs from folks who mentioned it. We're really thrilled and grateful to NASA STMD for this opportunity to demonstrate the first elements of LUNAGRID on the lunar surface. This project that you see here kind of encapsulates the overall effort. Most visibly, you can see the cables coming from the lander to the cube rover. So there's two sort of big elements that we're demonstrating. One is doing reeling and cabling on the cube rover and having that extend out from the lander. So demonstrating that capability. And then perhaps most importantly, actually demonstrating power transmission over those lines. So demonstrating 1 kilowatt over 1 kilometer and proving that that's possible on the surface of the moon. Perhaps what's not visible visually in this image is the power grid electronics that we're looking to also demonstrate, even do some AC-DC conversion demonstrations on the lander itself with some power electronics that we want to prove out for LUNAGRID. So this is we think kind of an opportunity to really demonstrate some of the capabilities that have maybe a little bit lower TRL, actually demonstrate them on the lunar surface, and then bring in all the other elements that I was mentioning earlier that are already under development, already funded today. So we really see this as a major step forward for LUNAGRID. And again, we're incredibly excited to begin executing on this project. This would be a payload project that would fly on an upcoming astrobotic lunar lander mission in 2026. So with that, I will stop there and look forward to the discussion. Thanks.
Fantastic. Very exciting to see all of this work that's going on, and it feels so tangible now. things are happening. So there's lots of great questions in the chat, and I encourage the audience to keep putting them in there. Some of them are being answered already. So the ones that are most directed towards particular panelists, let's get those. But I want to give everybody a chance to have something that wasn't in their prepared responses. So as active developers of these technologies now, maybe we could go through and hear which aspect of the system that keeps you up at night, reliability wise, and maybe we'll snake back through the order. So Dan or Dean, we can go to you first.
Oh man, I mean, there's a lot of it. The major issue for us that we see is the thermal issue. So in all these systems that we're talking about, one thing that's not mentioned very often is the thermal, and that is the thing that's going to be the deal breaker in a lot of cases. So laying cables sounds nice, and Dan's going to find this out soon, but cables on the moon generate a lot of heat, and it's difficult to get rid of that heat. So then you think about power beaming, and someone brought it up. Well, power beaming's even worse. So you have heat generated on the one side. So let's say, a kilowatt laser beam to get 100 watts at a rover, for instance. A kilowatt probably generates 5 kilowatts of heat. So you somehow have to get rid of that. And then you beam a kilowatt and only 100 watts is generated as electricity. So now the rover has to get rid of 900 watts, and that's a lot of heat to get rid of. So all of our systems, are going to grow, or have to think of really interesting ways of dissipating this heat in an environment where it's very difficult to get rid of heat. Most people are worried about cold on the moon. We're really worried about hot.
Right.
The heat is going to be the problem.
Let's go to, I think it was Joe who was next in our list.
Sorry, Wes, I missed the question.
Oh, no, it was asking, you're actively developing technologies now. What keeps you up at night for reliability?
So I think certainly from reliability, it's understanding for us, right, the ability to, in ideal circumstances, really fully test a nuclear solution on Earth and being able to deploy that in space. Some of the challenges we have, right, is not being able necessarily to do everything from a nuclear perspective that we like, and limitations on facilities and infrastructure. Certainly, obviously, our national labs have a ton of capability there. But as we look at, all right, how do we take a reactor? How do we launch a reactor into space? And how do we ensure that we've done everything we can for it to be the most reliable solution? Obviously, that goes into some of the original technology solutions and concepts. But I think what keeps me up at night is being able to demonstrate and convince both the public, NASA, the industry, that this is going to work, and convince ourselves as well that this is going to work, and how much testing can we functionally do to get there, understanding some of the challenges working with nuclear material.
Great. Luis, yes, you've got it.
So I kind of foot stomped this a bit during the presentation,
Yeah.
but it's really mostly the grid management context. I mean, there is a, the amount of problems that we need to solve here, and the causality of the interconnectedness of all them are basically our legion. But the context from a commercialization transition context, of what does the grid really need to look like, and how do we convince ourselves that we are comfortable having crew members that can rely on this power and take advantage of the system efficiency we're trying to achieve? That, there are a lot of ideas there, but the answer to that question is the scope that I think that keeps me up at night.
Okay.
In addition to all the other problems, but no.
Well, at least if you're up at night, you can maybe look at the moon if you're lucky, right? Think about it.
Yeah, that's true. Staring at you in the face.
And Dan.
Yeah, several things, but I think the first order consideration that keeps us up at night is making sure that we have access to the locations in which we want to put up VSATs in the first place. So as you can see in the architecture image, when it comes to reliability, having multiple VSATs is kind of the overall longer term thinking. So if some of the key locations that we want to get the best solar exposure aren't available because someone else is already there, and maybe somebody's already pitched their own vertical arrays. And I'm not talking about our industry colleagues here in the US side, I'm talking about maybe other nations around the world, and then maybe have restrictions where you can't operate or try to at least impose them. We, of course, would oppose that. That's a concern that we have. We really think it's very important that the US get to the surface, get to some of these key locations where there's not just optimal exposure for sunlight, but also are crossed with good locations for communications, and also good science and potentially even resource allocation. So it's really about getting there quickly and early to be able to take advantage, because if we have to wait until a nuclear asset is online, the US, I think, overall will be at a disadvantage, and it'll just take too long. And I think we might be passed by other challenging nations. So that's the thing that really keeps us up. And there's sort of several orders of concern, not just about power, but even just about US presence that are interconnected there.
Great answers, and actually really, a really nice complement of answers as well. So I want to ask a question. There's lots of great questions in the chat as well. I want to make sure that we, get those answered as we can, but also give, reasonable amount of adherence to our scheduled events. So one question that I have that I think would also be quite nice to hear more broadly from folks, and we'll go in the opposite order this time so that Dan doesn't always have the most amount of time to answer the question. So one question is, so here it is. What are some of the key things we need to be learning right now in these early missions, like what you were just talking about, that'll enable us to develop reliable power as we go on in the future? So basically what I'm asking is, what do you need to know next to ensure that we can achieve that reliable commercial power as soon as possible?
Yeah, I mean, I think in our mind, it's the latest award sort of speaks to that. And as Dean had highlighted too, it's not going to be an easy lift. Transmission via cables is really important, and we feel like compared to power beaming, which again we think will come online, but it's just maybe a little less mature for usage for distribution. We wanted to demonstrate transmission. We really feel like that's going to be important to be able to actually have a grid. All the other elements. And I don't want to be maybe too brash to say it's all figured out and already been demonstrated. It hasn't, but cables in our mind, like that's a soft spot that we really want to attack first.
So cables and their sort of interaction with the actual true lunar environment and all that comprises, which gets at several of the other questions that I think were being asked sort of in the chat. So Luis then.
So what ought we demonstrate first? So basically, so there's a progression.
So it could be either, yeah, basically I'm asking, it could be whether it's a knowledge gap that you need in order to be able to do the technology development here, or a demonstration. What do you need to know or do next to arrive at that commercial lunar power grid ASAP?
So I want to congratulate Astrobotics on their tipping point win for that deployment. It is the very first step, though, and so in the context of getting to Class A, we need a number. There's going to be a progression of demonstration that is needed, and the things that to get to Class A, to get to having power that astronauts can rely upon. The thing that I worry about most is the electrostatic effects and arcing in the context of these high power based designs, as well as the grid node infrastructure with respect to thermal design implementations. A lot of this, basically it's the daylight between what you can do in a TVAC chamber simulant and what you really need something boots on the ground in order to get feedback on.
Great, and then Joe, go to you. And let's all mute. I think there's an echo, so I don't. Yep, thank you very much. And Joe,
yeah, so I think a couple items that come to mind, I think, are certainly understanding the load profile and the load demand, the load follow requirements, change, control rate expectations, and how do we deal with load transients, loss of load, and between marrying the power system and the grid system. The other thing is really from a reactor fission power source perspective is also really having the capability and to understand really the launch process and the regulatory process. This isn't something the United States has done in decades, so and a lot has progressed there. So from our perspective, commercially, it's getting some certainty, and I believe the government teams are working on that. And I expect there'll be industry feedback periods and things like that will help form that. But getting more certainty and understanding for the long-term planning of this deployment that's a critical aspect as well.
Great, and then we can end with Dean. What do you need to know?
Going last is just as hard as going first. Yeah, all of the answers are really good, and they progressively stole each one that I had. But I think all of the technologies have a really good path to being developed. There is the development money put in place already to figure all of these things out, and all of the companies are great, and we know all of these companies are able to do it. I think the real issue is really getting the buy-in from NASA at this point. They are sort of bought in. I mean, if I'm being kind of frank, they bought in on the development side and pretty much totally bought in on the development side. The follow-on from that is very tenuous. we hear Congress talking about, mandating NASA to have power on the moon in a certain time frame, but the money's really not there. And as we see, more funding cuts to NASA, or different focuses within NASA, power feels like it's getting left behind a little bit, where power on the moon is one of the most important things that need to be demonstrated and need to be implemented.
Boy, that's a nice, strong statement to sort of finish out our panel. I will say one thing that I've noticed. I track this stuff pretty closely too. I think that I certainly commend NASA with moving towards Moon to Mars and trying to achieve some stability and resiliency of their own for the objectives that we have. And I think that you're right. There has a shifting of focus. At least quite recently, the focus has been coming more squarely on the moon. And at least maybe we can, I don't know if John is here or others want to be able to speak to it, but as you saw in the lunar and Mars infrastructure blueprint objectives, power was the top objective for both of those. And it was, in very specific NASA language, to develop, which is deliver the capability to the end user, the scalable incremental power grid. So I think that you're right that buy-in is essential, and I think that we're on the path, and the things that we're doing now, I think, are the things that need to happen to make sure that we continue to solidify that, right? So a wonderful way, I think, to end that session, which means I'll now be able to pass on for our lightning talks to hear more about some specific technical details of all of these efforts. And Julie has come off, yep, we've got her video now. So Julie, I will let you take over. Thank you very much again to our panelists. Please, you can answer some more of the questions in the Q&A before you dial off if you have time. And I very much appreciate your time and your comments. So thank you again.
Thanks so much, Wes. And again, fantastic panel. Thank you so much to everybody who was speaking there. Really awesome talks.